In this video, we're going to look at organic chemistry mechanisms. So our specific goals are to be able to draw arrow-pushing mechanisms, so-called arrow-pushing organic chemistry mechanisms for biochemical pathways, in particular, biochemical reactions. Second, to classify nucleophiles and electrophiles. And third, to recognize and show mechanisms for a few specific examples in biochemistry, such as enol formation. Okay, so let's jump in. So the curved arrow formalism in organic chemistry is used to show the flow of electrons. So when we talk about drawing a mechanism or proposing a mechanism for a reaction, we're talking about drawing the flow of electrons using the curved arrow formalism. So that means that the arrow is showing you where the electrons start, like in this case the electrons, the lone pair on the amine, on methylamine, is acting as the nucleophile. These electrons are then moving over to grab the hydrogen nucleus, the proton, without its electrons, just the proton. And then the electrons that are in this bond, 2 electrons in every bond, so there are 2 electrons in this hydrogen-oxygen bond. Those 2 electrons are now moving, as this arrow shows, onto the oxygen. So the electrons end up where the end of the arrow is. In this case, they're moving from the nitrogen to form a bond with the hydrogen, and then with the proton, and then the electrons in the hydrogen-oxygen bond are moving away from the hydrogen onto the oxygen, breaking that bond. So again, in this case, the electrons are on the methylamine lone pair, on the nitrogen, so that nitrogen is the nucleophile. And the electrophile in this reaction is the proton. It's electron deficient, so it's able to accept those electrons. The product of this particular reaction, this is just a protonation where we're transferring the proton onto the nitrogen. We get the protonated form. And now if we were to run the reaction in reverse, the conjugate base, acetate now, would act as the nucleophile because the electrons are on the oxygen. We could draw an arrow grabbing the proton, and then the electrons in the hydrogen-nitrogen bond would go onto the nitrogen with that arrow. So in that case, the conjugate base oxygen of the acetate would be the nucleophile, and the conjugate acid, the proton, protonated amine, would be the electrophile. So the nucleophile is always the species that is donating the electrons, and the electrophile is the species that is receiving the electrons. So we can think about that from the orbital standpoint. If there's an orbital, like the nitrogen here, with a lone pair, 2 available electrons, a filled orbital, that is available for attack, not tied up doing something else, then that would be a nucleophile. An atom with an empty orbital, a vacant orbital, can act as the electrophile. In this case, the nucleophile is a base, methylamine, and the electrophile is a Lewis acid, but the principle is the same. So here's just a definition, maybe if that helps think about this. What are electrophiles and nucleophiles? So an electrophile is something that's electron loving. It doesn't have enough electrons, it's ready to receive them. It's something that is positively polarized, it's electron poor, and it's ready to form a bond by accepting a pair of electrons from something that's electron rich. So nucleophile is the opposite. A nucleophile is the atom that is electron rich. It's nucleus loving. It has a negatively charged electron rich atom, and it can form a bond by donating those electrons. So in this case, in the example we saw in the last slide, electrophiles are the Lewis acids and nucleophiles are Lewis base. But in general, electrophiles are electron deficient and nucleophiles are electron rich. So let's see that type of reaction again. a proton can be a nucleophile, just as we saw before. So here's a proton, acetic acid. Now we could have some generic nucleophile with a lone pair, an electron-rich nucleophile. We draw the arrow going from these electrons attacking the proton. That means that the proton here, without any electrons, is going to form a new bond with the nucleophile. So we end up with the protonated nucleophile. And the electrons in the oxygen-hydrogen bond are now going to move. They have to go somewhere. They're going to move on to the oxygen. And that puts a negative charge on that oxygen. That makes this carboxylate. A methyl group can actually act as an electrophile in some cases if it is attached to a positively charged atom. We see this in biochemistry sometimes. We have a methyl group attached to a positively charged sulfur. So now an electron-rich atom, a nucleophile, can come in, attack the carbon, which is relatively electropositive here, and then we can push the electrons breaking the sulfur-carbon bond onto the sulfur. That makes a neutral sulfur because it started out as a +1 formal charge. So now with the minus charge of these 2 electrons coming in from that bond, it's now got a neutral sulfur and a positively charged nucleophile. So that's actually what we would call a methylation or methyl transfer reaction, where we're transferring the methyl from the sulfur onto the nucleophile. The carbonyl group often reacts where the carbon of the carbonyl group is acting as an electrophile. That's because if we look at the carbonyl group, oxygen is pretty electronegative, so it has these 2 lone pairs, and it is relatively negatively charged. So it is more likely to act as a nucleophile, whereas the carbon, because a lot of the electron density is being pulled onto the oxygen, the carbon is now relatively positively charged, and so it's a good electrophile. So in other words, these electrons from the carbonyl carbon-oxygen bond can move on to the oxygen readily, making that carbon act as a good electrophile. We could see that down here. If a nucleophile attacks the carbon, we can push the electrons from the double bond onto the oxygen, and that gives us now a single bond to the oxygen with a negatively charged. The nucleophile is attached to the carbon. That's a tetrahedral intermediate because of these 4 atoms now attached to the carbon. And again, a nucleophile could attack a ketone, for example. We'd push the electrons from the carbonyl group onto the oxygen, and now we would have this tetrahedral intermediate where the ketone carbonyl is now just a carbon-oxygen single bond. It's a negative charge on the oxygen, and the nucleophile has formed a new bond with that carbon. So we see this kind of reaction many times in biochemistry. Now, how do ketones and aldehydes react? Well, one way they react we just saw. The carbon can be an electrophile. You can add a nucleophile into the carbon. But there's another major way that ketones and aldehydes react, which is by forming a tautomer, another isomer, where we remove the alpha proton. That's the proton on the carbon that's adjacent to the carbonyl, alpha to the carbonyl. That makes what's called an enolate ion. If we protonate that with a hydrogen and this on the oxygen, that's an enol, a double bond ene, alcohol, enol. If we have the charged form here without the proton, it's called an enolate because of the charge. So when we remove a proton, we generate this enolate. The enolate is reactive. It's electron rich. We can see now it has the negative charge, and it's actually reactive usually at the carbon. So this carbon is now nucleophilic, and it can add into various groups. So it's important, it's really critical to remember that ketones and aldehydes can go into this enol form. These 2 species differ only by the movement of the proton. The proton's either on the oxygen or on the carbon. if we have the ketone or the enol form. So they're said to be tautomers. That's an example of tautomerism, which is defined by the Oxford English Dictionary. I always like to use the Oxford English Dictionary. It's the definitive source or reference of the English language, as they say. Tautomerism they define as being the property exhibited by some organic compounds of behaving in different reactions as if they possess two or more different constitutions. That is, as if the atoms of the same compound were arranged in two or more different ways. So basically, we can have the proton either on the oxygen or the carbon, and it's two different species moving back and forth very rapidly. Now the ketone form is a lot more stable, but the enol form can be much more reactive. It is in terms of the carbon acting as a nucleophile. So that is to say, the alpha carbon of a ketone in the enol or enolate form often acts as a nucleophile. So we'll look at a couple examples. So pyruvate, this metabolic intermediate or hub that we often see in metabolism, pyruvate has an alpha carbon here. So it has a ketone. Adjacent to the ketone is an alpha carbon with its adjacent proton not shown. If we remove a proton from this alpha carbon, just as we saw here, we make the enolate form. Okay, so that's the enolate. That's the reactive form. The enolate of this pyruvate could then attack an electrophile. For example, it could attack carbon dioxide. This is an example in the biosynthesis of oxaloacetate during gluconeogenesis. So the way that works, just to show you the whole thing, is that bicarbonate is a source of carbon dioxide that will decarboxylate or generate carbon dioxide. And then the pyruvate enolate will attack the carbon. So the enolate nucleophile is the carbon of the enolate here on pyruvate. It will attack the carbon of carbon dioxide. The carbon member is going to be the electrophilic atom. And that will put the carboxylate on to pyruvate. So we've made a new bond between what was previously the pyruvate alpha carbon and the carbon dioxide or the carboxylate. So this is now oxaloacetate. So this is the way that oxaloacetate can be synthesized from pyruvate and bicarbonate. Here's another example. Propionyl-CoA is used to synthesize succinyl-CoA. Now the way it works is we have to get a carboxylate on the beta carbon, but the beta carbon is not reactive. It's the alpha carbon that can form the enolate, and that's the reactive carbon. So propionyl-CoA can form the enolate form. Again, the alpha carbon's deprotonated. It can attack carbon dioxide. We make the carboxylated form that's shown here. That's called methylmalonyl-CoA. So we've got the carboxyl on the alpha carbon. And if we stop there, that would not get us to succinyl-CoA. But now there's an enzyme that can isomerize this, migrate the carboxyl group onto the beta carbon. But it doesn't initially react with the beta carbon because that's not the reactive carbon. And yet another example of the alpha carbon of a ketone acting as a nucleophile is in the biosynthesis of citrate during the TCA cycle. So now we have a thioester, not a ketone, but a thioester, but very similar in that we have a carbonyl group. If we make the enolate form of acetyl-CoA by deprotonating the alpha carbon, that can attack the ketone carbon of oxaloacetate. So this carbon, again, because it's in a ketone, it's electrophilic, it's a good electrophile. The enolate form of acetyl-CoA is going to be the nucleophile, specifically the carbon of this enolate, that can attack the ketone of oxaloacetate. And now we formed a new bond between, you can see color-coded here, the acetyl-CoA alpha carbon and the ketone carbon of of oxaloacetate. So we formed a new bond there, and that gives us citral-CoA. And then if we hydrolyze the thiol of CoA off of here, we get just citrate. So what about other kinds of mechanisms? So another common one is isomerization between ketones and aldehydes. So that often involves a so-called enediol intermediate, but it's the same exact reaction we just saw. It's enol ketone tautomerization. So let's say, for example, we have glucose. We have this aldehyde of glucose. If we deprotonate the alpha carbon with a base, we can generate the enolate form. If we protonate that, we have the enol form. So look here on the right, we made the enol form glucose. We have the double bond and the OH. This is the enol form of glucose. But interestingly, the enol form of glucose is also the enol form of fructose, because fructose would have the ketone, the carbonyl on the 2-carbon. It would be a ketone instead of an aldehyde that we see in glucose. Remember, the only difference between glucose and fructose is the aldehyde versus the ketone, the position of that carbonyl. To get from one to the other, we can go through this enediol intermediate. In other words, the enol of glucose is actually the same enol of fructose. They share this common intermediate. And then if we tautomerize from the enol back to fructose here by deprotonating the alcohol on the 2-carbon and protonating the double bond, we get fructose. So you go from glucose to fructose via this enol intermediate. It's just that it's an enediol. It's an enol with 2 alcohols. And so it's the same enol intermediate for glucose and fructose. What about the aldol reaction? So that's another example of an enolate attack. So if you can get this enolate chemistry down, if you're familiar with that, you'll see all of these mechanisms are basically very similar. So again, let's say we have a ketone. A base can deprotonate the alpha carbon. So that's the nucleophilic carbon. We now have the enolate formed here. The enolate then attacks, for example, an aldehyde in an aldol reaction. The carbon of the aldehyde is electrophilic. Carbon, remember, is going to be the electrophile now. And the enolate attacks. We push the electrons from the aldehyde carbonyl onto the oxygen. And now we have this intermediate where we have the tetrahedral intermediate on what was the aldehyde carbon. And we've added in this new carbon-carbon bond. Now, if we protonate that, we get this beta-hydroxy compound. So the product of an aldol reaction, what was the aldehyde is going to become a hydroxyl group. So we're going to end up with a beta-hydroxy compound. That's always going to be the product, unless it dehydrates, and then we'd have this double bond in this position. Going in the other direction, I should say, is the retroaldol. So if we have a beta-hydroxy compound, we deprotonate that, we can cleave this carbon-carbon bond and generate a molecule that's shortened by these 2 carbons. So that's a retroaldol reaction. It's a bond cleaving reaction. That's what we see in glycolysis as well. Nucleophilic substitution reactions are also common in biochemistry. So a nucleophilic acyl substitution reaction is shown here, where we have a carboxylic acid type structure, maybe it's an ester or an amide, and then a nucleophile can add in to the electrophilic carbon. Again, the carbon's going to be the electrophile. The nucleophile comes in, attacks the carbon. We make that tetrahedral intermediate. That's not shown here. And then we eliminate Y, this leaving group. So now the nucleophile has replaced Y in the structure here. So it's a substitution of Y for the nucleophile. So what's an example of that? Well, in the conversion of this aldehyde to a phosphoanhydride, we see the aldehyde can be an electrophile. For example, an enzyme thiol can add into that aldehyde. We get the tetrahedral intermediate. Now the leaving group in this case is going to be hydride. We're going to kick out H-, this hydrogen with its 2 electrons. And so in order to do that, we need a cofactor NAD+. NAD+ receives those electrons, and we get the carbonyl reform, but now as a thioester. Before it was an aldehyde. Now it's a thioester. We've actually oxidized that carbon to the level of a thioester, and now inorganic phosphate can attack and do the nucleophilic substitution reaction by replacing the enzyme thiol. Those are about energetically equivalent, and we end up with the phosphoanhydride. So this is actually used in glycolysis, where we have glyceraldehyde 3-phosphate as the aldehyde. The enzyme thiol attacks. We kick out a hydride onto NAD+, forming NADH. We make the thioester, and then the thiol gets exchanged for inorganic phosphate to make the phosphoanhydride. That's 1,3-bisphosphoglycerate then as the product. And what about decarboxylation? So that's another common reaction. In this case, we need a good electron acceptor always on the beta carbon. So in this case, if we oxidize the beta carbon to a ketone, that makes a good electron acceptor. And so now we can decarboxylate, lose carbon dioxide, and end up in this reaction going from isocitrate to alpha-ketoglutarate, where we've lost 1 carbon, gone from 6 carbons to 5 carbons. Okay, so to summarize, in this video we learned about recognizing nucleophiles and electrophiles and drawing reaction mechanisms with arrow pushing, such as carbon-carbon bond forming reactions and isomerization reactions.